So in problem 1 of this video 3 assignment, what are we trying to do? We're trying to see if we can understand a way of adding up an infinite number of numbers that are all positive. Your first instinct might be that an infinite number of numbers that are all positive would have to add up to an infinite amount. It would have to be more than 1,000, more than 1,000,000, more than 1,000,000,000. But in fact, we're about to show that this is not an infinite amount. In fact, it's not bigger than 1. It's pretty close to 1, but it's not bigger than 1. And one way to do this is to try adding. So let's try adding. So if we add the first term by itself, we get a 1/2. If we add the first two terms, and this is going to require some skills, we're adding 1/2 plus 1/4, but that's 2/4 plus 1/4, because 1/2 and 2/4 are the same, and that's 3/4. So if we add up the first one, we get a 1/2. If we add up the first two, we get 3/4. And we're just going to keep doing this. We're now going to add up the first three. So we have 3/4 plus 1/8. That will be 6/8 plus 1/8. That's 7/8. So when we add up the first three numbers in this long addition problem, we get 7/8. Now when we add up the first four numbers, we'll do the first three, which was 7/8, plus the next one, which is 1/16, and that's 14/16 plus 1/16, and that's 15/16. And I could do the next one by adding 1/32 and the next one by adding 1/64, but I'd like to see if you notice a pattern. 1/2, 3/4, 7/8, 5/16. Could you predict the next one? Well, it looks like the bottom numbers are going 2, 4, 8, 16, 32. That's not too amazing because these bottom numbers are going 2, 4, 8, 16, 32. And it looks like the numerator is always 1 smaller than the denominator. So 2 take away 1 is 1, 4 take away 1 is 3, 8 take away 1 is 7. It's always, so it seems to me like this would be 31. And if you grab a calculator and do the division here, this will be 0.5, this will be 0.75, this is 0.875. And so on and so forth, and these numbers are getting closer and closer to 1, but that really doesn't tell us what I want to know. Notice that the bottom number is always 1 bigger than the top number, so these fractions are never going to be as big as 1. The next one will have 64 on the bottom and 63 on top. So as we keep adding and adding and adding and adding and adding forever and ever and ever, the fraction that we get when we do all that adding has to stay smaller than 1. Therefore, this thing does not grow to infinity. Therefore, it's finite. Before you panic, this is one of the problems that you're supposed to do for V3, this exact problem. So you listen to this, you think about it, you organize your work, maybe try to make it more organized than mine, and do it. And try to understand that we just proved that this adds up to a finite number that's not bigger than 1. And this exact problem is what the V3 assignment is, problem 1, and you should be able to do it. So our next problem, and our last problem on this assignment, is to look at this sum of numbers. It's an infinite number of numbers being added, and they're all positive, and to try to figure out what's going on here. Now, you'll notice that all the numbers in the previous problem, problem 1, are here. We have the 1/2, we have the 1/4, we have the 1/8, we have the 1/16, and so on. But this has more numbers in it, extra numbers, so probably this sum is going to be bigger. The question we want to ask ourselves is the sum finite? Or does it just keep getting bigger and bigger and bigger forever so that, it's bigger than 1,000, bigger than 1,000,000, bigger than 1,000,000,000, etc.? And the answer is going to be that it's bigger than any number we choose. It's infinity in essence. But how do we know that? Well, I want to show you a trick, and your job is to learn this exact trick on this problem and be able to reproduce it on your homework and on a test. There's not going to be problems like these two problems. It's going to be these two problems. So if we're trying to show that this goes upwards forever, kind of to infinity, what we're going to do is we're going to create a sequence of numbers that's easier to work with. And we're going to show that this sequence of numbers that's easier to work with is smaller than this one, and the smaller one goes to infinity, gets way big. And that means the bigger one has to get way big. And then we're done. So I'm going to keep the 1/2. And I'm going to take the 1/3 and I'm going to make it be 1/4 instead. Of course, I'm going to keep the 1/4. There's no of course about it. Why would I do that? Now, what am I going to change 1/5, 1/6, and 1/7 into? I'm going to change them into 1/8. So the 1/5 becomes 1/8, the 1/6 becomes 1/8, the 1/7 becomes 1/8, and the 1/8 stays 1/8. So for each one of these numbers, I'm either leaving it alone or making it be that next power of 2. So I made this be a 4th, kept the 1/2 and the 1/4. I made each of these be an 8th, kept this 1/8. Now each of these is going to be a 16th plus this 16th. So I'll have a 16th plus a 16th plus a 16th plus, sorry for the messiness, I'm still not quite used to this way of writing. 1, 2, 3, 4, 5, 6, 7, 8. Forever. So what does this 1/1/2 equal? It equals a 1/2. What does the 2 1/4 equal? It equals a 1/2. What does the 4 1/8 add up to? It adds up to 4/8, which is 1/2. What does the 8 1/16 add up to? It adds up to 8/16, which is 1/2. The next one will be 30 seconds, and there'll be 16 of them, and that'll be 1/2. And it keeps going forever. And so what we find out is that our new sum, this one, the easier one, that's designed to produce these 1/2s, it grows forever, because this is 1 plus 1 plus 1 plus 1 plus 1 plus 1 forever. It just gets bigger and bigger and bigger and never stops growing. It passes up 1,000,000, passes up 1,000,000,000, passes up any number you can think of. So this thing is really growing unboundedly to infinity. But every single one of these fractions in the original was either the same, like the 1/2s are the same, or it was bigger, like 1/3 is bigger than 1/4. Now you may need to think about that. Several people do. Why is 1/3 bigger than 1/4? Well, if you have 1/3 of a pizza, you have more than if you have 1/4 of a pizza. That's one way to look at it. The 1/4 stayed the same, but each of these is bigger than 1/8. So we have a bigger number than 1/8, a bigger number than 1/8, a bigger number than 1/8, and an equal number to 1/8. So term by term, number by number, these are all equal to these down here or bigger. So if this smaller sum grows forever, then this bigger sum has to also grow forever because it's bigger, and it means it goes to infinity. So these are the two problems you need to do on your wait a second. I was distracted. It looked like I was out of time on this video, but I was looking at it wrong. Sorry. The two things you need to do are these two problems. You don't have to talk to me. You can just show me the steps, show me the work, show me that you know what the goal is. In the first problem, showing that it's finite because it's always smaller than 1, and showing that this one's infinite because it's bigger than another series that we made that goes to infinity. And you have to reproduce this. You don't have to think of it on your own. You don't have to do problems like this. So this V3 assignment is really pretty straightforward. You can do it and remember it, because one of these will most likely be on the first exam that you take, which won't be for a while.